Good afternoon, everyone, and welcome to this session on Imperas fast processor models. I'm going to spend a little bit of time talking this afternoon about why high-quality, high-performance software models are such an important part of anything you want to do in RISC-V today. I'm going to start by introducing some industry trends, and you'll recognize some of the material because it was used earlier as well by another presenter, which kind of reinforces just how important it is. Talk about why we need fast CPU models, where we use them, a little bit about what makes them fast, and then talk about CPU verification as well, which is, you'll see why it's related to models and why it's become such a hot topic as well in the RISC-V world, before we wrap up and draw some conclusions. So, looking at industry trends, this chart on the left, it was showed earlier, I'm sure you'll have seen it in other presentations elsewhere as well. It's being used more and more these days to recognize the challenges of scaling we have today. And while the number of transistors on devices continues to increase, single thread performance has run out, and we're seeing more and more multi-core platforms appearing. And the last few years, these have probably been SMP systems, 4, 8, even 64, maybe 128 core systems. But the change now with some of the AI applications we're seeing, and there's an example here on the right from Meta, who announced their MTIA last year, is we're now seeing arrays of processors that are communicating with each other, working with each other, but they're not necessarily running Linux. They're not necessarily a traditional SMP scalable system. So the ability to model that and work out what your software is going to look like, how your software is going to run, what your system architecture looks like, becomes increasingly important with these changes we're seeing in the industry and rise of AI applications. So when we look at some of the other things going on, we're seeing new data types coming along. bfloat 16 is now probably almost commonplace. We're seeing other custom data types appearing, and the joy of RISC-V is you can customize, you can add instructions to deal with your custom data types. And the other side of it is that the software is evolving much, much faster than hardware. If you think about how long it takes to develop and tape out a chip and get silicon back, you're talking, probably at least a year, while software algorithms are evolving on a weekly and monthly basis. So as a designer, you're having to think about building hardware for software that doesn't exist yet. And that's where, again, having the right sorts of models, being able to see how your system works, trial your software, experiment with it is so important. The final change we're seeing is verticalization. So with this interesting custom silicon, with this ability to customize and roll your own solution, we're seeing more and more companies want to own hardware and software stacks and develop their own custom chip for their own custom workload. So how do models help with this? Well, first of all, if we think about earlier software development, I said the cycles are getting faster and faster. If you're having to wait not only for your silicon to get back, but only then starting software development, your time to market is going to be really, really slow. So by having fast, performant, accurate software models available, you can shift left and start your software development earlier, so that when the silicon comes back, you're ready to go into production straight away. And there's some examples here of that scaling problem with complexity, looking at how long it takes to boot Linux on different types of simulation environment, from an RTL simulation at a few kilohertz, taking days of simulation time, through to emulators and FPGAs, taking maybe hours and minutes. If you're running on a sufficiently fast software model, you can boot that Linux in seconds. It's not quite real time, but it's very, very close. And that means you can do real useful software development on that platform. The next side of it is architecture exploration. We all know that RISC-V brings that freedom to innovate. You can add your customizations, you can add custom extensions, you can select from the standard extensions that are available. But if you're going to do that, you need to be able to iterate quickly. So you need to be able to change your design, look for performance improvements, and iterate on a quick basis. And you need something that's easily extendable, and you need something that you can profile and analyze to see what benefits you're getting. And the way the Imperas fast processor models have been architected means that there's a strong, rigorously tested base model. It's customizable, it's configurable, so you can choose which of the standard ISA extensions you need. You can add your own custom extensions to that as well. If you couple that with the verification, analysis and profiling tools we have, it's very easy to run through your custom software workloads, find the hotspots, optimize them and test that in a simulation environment. So we see that RISC-V is enabling these new CPU designs, it's enabling customizations, but the swing side of that is you need to make sure it's going to work. You need a strong verification story. And we all know that verification is taking more and more of the design time, and at CPU level that adds another level of complexity due to the state space complexity compared to traditional SoC development. If you have a high quality golden reference model, you can integrate that into your verification flow and use that to help you verify that your design is behaving correctly. You can also use it in a hardware assisted verification environment, so not just running on an RTL simulation, but actually running with an emulator platform to give you a speed boost so you can get through the number of cycles you need to reach sign-off. So when we think about what makes the model fast, the underlying technology is a JIT simulator. So we're doing binary translation of the RISC-V instructions to the host x86 instructions. The architecture of the simulator and model has been designed over many years. It's a very clean and separate interface, so the changes in the model don't interfere with the simulator. Performance enhancements in the simulator don't compromise your models. And that scalability with open APIs that are publicly available means it's very scalable and extensible. It's very easy to deal with different versions of extensions as the RISC-V ISA evolves and matures. And it also means the end simulator scales linearly with the number of cores. So if you're now simulating a 64 or 128 core platform, you get the sort of equivalent total number of MIPS for your system simulation. There's no penalty falling off a cliff simulation-wise just because you've got a large number of cores in your simulation environment. So I touched on verification earlier and said it's the next frontier of things to worry about. But why is it so hard? What's different about CPU verification? Historically, you'd license your IP from someone and they've done the hard work, but all of that was their secret sauce, all of that was proprietary. And users who were used to pre-verified IP now have to do that verification themselves. Because RISC-V is so configurable and customizable, you have to verify both the base ISA, but all of those extensions too. And the DV techniques are not well known. It was often secret source of the other IP developers, and ASIC and SoC verification techniques are not directly applicable to CPUs. When we came to look at this, we found there were no commercial solutions available, and so created ImperasDV, which is now Synopsys ImperasDV, to fill that gap. And to give you an idea of the scale of the problem, I'm going to look at some functional coverage data here, as that sort of speaks to the scale of the challenge when you're looking at CPU verification. So let's take one instruction. It's a simple instruction, an add instruction. You've got two inputs, one output. That generates about 10 to 30 cover points of all the things you want to care about. You want to check you've tested all the source registers, whether the source and destination overlap, whether the two source registers are the same, ranges of values, max, min, overflow behavior, all these sorts of things. So that gives you about between 10 and 30 cover points depending on the instruction. And then for each of those cover points, you need another 20 to 40 lines of system Verilog. So if you scale that up, if you have something like a RISC-V 64 GCV applications class processor, there's maybe 1,000 instructions in that. So that means you need 300,000 lines of system Verilog functional coverage. And not only do you need that coverage, you need tests to hit it as well. Doing that manually is going to be very error prone, very slow, and doesn't scale. And so we have some unique solutions that can help generate this for you to achieve that coverage you need. So to wrap up, Synopsys ImperasFPMs are really at the heart of RISC-V. No matter what it is you're trying to do with your processor development, some element of that is going to touch on models, and we've got a solution for you within that, whether it's from the basic architecture exploration through compliance testing, verification, performance analysis, and even full SoC simulation environment so you can try your production software. So to recap, RISC-V needs these scalable modeling solutions to be successful, whether it's architecture exploration, software development, and CPU verification, and the ImperasFast processor models meet all of these needs. I'd like to say thank you for your attention, We're giving some other talks over the next few days of the show as well. We're here on the booth, so if you want to come and talk to us, find out more, please do that. Thank you very much, and I think we've got a few minutes for questions.